Having completed the static rigging and rigged both engines to be physically the same, it is now time to see how they are matched when we run them in the engine run bay. The aircraft maintenance manual should be referenced for the settings required, which should be written onto an engine run sheet. Having set the deadband in the hangar, we have a good idea of what to expect in the engine run bay. Slowly advance one power lever at a time and mark on the tape the point at the compressor speed begins to increase. Now pull the power lever back to the flight idle gate and again mark the tape. This shows the amount of forward deadband. Slowly pull the power lever from the flight idle gate to the ground idle gate and mark this point on the tape. Continue pulling the power lever toward reverse to the point at which the compressor speed begins to increase. Mark this position on the tape. This shows the amount of reverse deadband you have. Operationally, we want to rig twin-engine aircraft based on matching engine torques and having no split in the power lever knobs. Therefore, we need to adjust the rigging to provide the compressor speeds that give us matched torques. Select 4 or 5 target torque values that cover the power range for the aircraft. These become the points that we check the knob split. Increase the power on both engines together, mark the position of the power levers at each of the target torque values. As you see here, there is about half a knob split at the higher torques. Let's take a close look at the type of knob splits possible. The progressive power lever stagger. For illustration purposes, we've set up 20% torque on either engine and we have a minor power lever stagger. As we advance power, again matching torque, the stagger becomes a little bit more progressive. As we continue to advance power, the stagger becomes very progressive now, very pronounced. To correct a progressive knob split, the serrated washer is used. For a lagging knob, on the right-hand engine, index the serrated washer in a clockwise direction, about 4 serrations to correct half a knob split. For this example, the constant power lever stagger, again we've set up 20% torque on either engine and the power levers have a stagger at 20%. The stagger remains the same as we advance the power to 40% on either engine. It stays the same at 60% and it stays the same at 80%. To correct a constant knob split, lengthen or shorten the fuel control unit interconnect rod by one half to 1 full turn. In our case, we will lengthen the rod, which will reduce the knob split by requiring a higher power lever position to get the compressor speed required for equal torques. After making adjustments, the test is then repeated. The tape is again marked as torque is increased to check the change in response. In this case, we can see the knob split we originally saw has now been eliminated. If this is not the case, we would then make further adjustments as indicated by the tape. Remember that for all running checks, the serrated washer adjustment is always the fine adjustment and never the coarse adjustment. To check the rigging in reverse, slowly pull the power lever into reverse and all the way back to the maximum reverse stop. What you are looking for on this installation is that the compressor speeds meet the aircraft maintenance manual setting limits at the full reverse position. Record the compressor speeds and torque values at maximum reverse. Ideally, they should be well matched. Whether this check is done on one engine at a time or both engines together, the goal is to meet aircraft maintenance manual limits for compressor speed while having both engine torques closely matched for improved aircraft handling. The engines in this aircraft are meeting the aircraft maintenance manual compressor speed limits and are well matched in torque. If you need to adjust compressor speed in reverse and better match engine torques, the reverse stop on the fuel control unit should be adjusted in to increase speed and torque and out to decrease speed and torque. Any adjustment made to the deadband screw will have affected the low idle speed setting. Check the low idle compressor speed and make any adjustments as required. To adjust the low idle setting, first loosen the clamping screw. To increase idle speed, first loosen the right hand screw, then tighten the left hand screw against the tab. To decrease idle speed, first loosen the left hand screw and tighten the right hand screw against the tab. Note that the adjustment is quite sensitive. We show it here greatly exaggerated for demonstration purposes. Tighten the clamping screw. Check the high idle speed with the condition lever advanced to the high idle position. Prior adjustments made to the condition lever maximum stop for matching lever travels will have affected the high idle speed. Adjusting the high idle compressor speed is done by loosening one nut and tightening the other. Moving the roller toward the high idle cam increases compressor speed. Moving it out, away, decreases compressor speed. Check and adjust the maximum compressor speed using the tool defined in the aircraft maintenance manual. To reduce the maximum compressor speed, turn the maximum stop speed screw counterclockwise. To increase maximum compressor speed, turn it clockwise. Note that this is a sensitive adjustment and is shown exaggerated here for demonstration purposes. With the propeller levers fully forward, increase engine power to bring the propellers up to governing speed, per the aircraft maintenance manual requirement. For this aircraft, 1700 RPM. Check the speed of both propellers and listen if they are synchronized. Listening to the engines at maximum propeller speed with the propeller synchronizer disengaged will confirm whether the propeller speeds are the same or not. Small adjustments of the maximum speed stop screw will eliminate any annoying out of sync noises. To check this setting, secure the propeller governor reset arm on the reset rear stop. Run the engine, set the propeller levers to maximum, advance the power levers and confirm the propeller speed is 95% of maximum selected. In this case, the right-hand engine speed is too low and needs to be increased to meet the aircraft maintenance manual requirements. To make the adjustment, loosen the locking screws and turn the adjuster counterclockwise. This is a sensitive adjustment, and turning the adjuster about the width of a slot will change the propeller speed about 50 RPM. In this aircraft, the flight idle blade angle check is performed at 1500 RPM propeller speed, and the torque verified to see that it meets aircraft maintenance manual limits. This check confirms that the propeller fine pitch stops, the beta nuts, and the beta valve rigging have been set correctly. Small adjustments may be made to the system as defined in the aircraft maintenance manual. By paying careful attention to the static rigging and understanding the basic adjustments as detailed here, during the running checks, both engines can be matched together. It will take some practice for you to discover your own personal shortcuts, but by applying the basic aircraft maintenance manual procedures and the workflow shown here, rigging engines will no longer be an issue.